awesome documentary. I recently saw an awesome documentary on archaeoastronomy. What is the policy about showing a movie from Prime?
We can do it as long as it's permitted by the presenter. But let's talk about that, offline or after the meeting, because we're up at 8 o'clock and I want to give our presenter all the time he wants. With that, I will invite everyone to stick around after the presentation if they'd like. We usually chat for a bit. One of the things we do during the presentation is, generally speaking, although I forgot to ask this of our presenter, maybe he can address it when he comes in, is turn off the video, because if you have a question, it helps if you turn it on. It's a louder way of announcing your presence and a wish to ask a question than just raising your hand, or sometimes even typing it in the chat, although please feel free to do those things. It's just that we might not notice it right off the bat. It's also very helpful if you mute your microphone once the speaker starts. With that, I'll hand it over to Alex to introduce our speaker for tonight and call the meeting of June MHAA closed. Thank you.
Okay, so our speaker tonight is Kevin Lloyd. The title is Radio Telescopes 101. He is living in Denver, Colorado. He has been working with radio telescopes of his own design for the last 15 years. But his inspiration came from an event that happened in middle school. This is a great story. In middle school, he was an avid optical astronomer, but was always curious about radio astronomy. But naturally, he thought it was too complex and expensive for him to undertake. One day, he was in the school library and stumbled on a book that described how to build a radio telescope using an FM receiver. He was fascinated, but he was also late for class. So he put the book back with the hopes of checking it out and studying it. The next day, searched and searched, but never saw the book again. But he remembered what little he read all those years ago and have discovered for himself just how simple and easy it is to build a radio telescope. That's it.
Well done. Thank you, Alex. Can you guys hear me?
Yes, I can hear you.
Okay, great. Hi, I'm Kevin. Let me share my screen. And share that screen. Okay, can you see my slides?
Yes.
Is that a yes? Okay, good. Thank you. This right here is probably not what we're going to talk about. This is a pretty fancy radio telescope array. And the reason why I have it up here is because, well, like I said, it's not what we're going to talk about. You don't need big fancy equipment and multi-million dollars worth of computer equipment and to analyze things. Really, to get started, you need just basically an FM receiver or an AM receiver. That'll work. But just like Alex said, my inspiration started when I was young, and I remember just how, the basics that I had remembered, and it wasn't much. Believe me, it just wasn't much what I remembered, and that really did help me. I would have thought it would have been a hindrance, but it helped me because of the fact that since I knew so little, that's all I could rely on. And when I did, I came to learn for myself just how basic it is. So I have no training in radio technology, so to speak. I just got a job in wireless though. So I'm going to have to take this part of the slides out. But my point is if I can do this, anybody can with no degree and no specialized training. And all you need to know is just some key concepts that we're going to talk about tonight. Let me go back. You guys see this right here? You guys recognize this, right? It's Galaxy Center. We all know that. But that's was the beginning of radio astronomy. There was a guy named Carl Jansky who pointed a shortwave radio in that direction and saw the power of his radio go up, and he heard the hissing get louder, And that's when he realized, hey, there's noise coming from this area. Excuse me, can somebody mute? All right, thanks. And so that was right here is really the beginning of the radio astronomy. This was what started it. So here are the basic concepts. You have three basic components, and I read this back in middle school. A receiver. Okay, I think you guys are smart enough to have figured that out on your own. You didn't need me to tell you that. The next component is an antenna, and I'm pretty sure that you would have figured that out soon enough, that you need the antenna. And then the last component is called a recorder. And that's because what you're going to hear out of the receiver is white noise or a hissing sound. And that's just no fun to listen to for hours on end. So you need something to record it. And then you can go back later and review it. And that's it, really. I made my first radio telescope probably for less than $200, buying stuff at garage sales and picking things out of trash. I'm not proud of that, but hey, you can save money. And so there's just really nothing complicated about it. Once you know how to apply these basic concepts, you're on your way. So let's talk about how it works, because most people aren't really sure about what to expect with a radio telescope. You're not going to hear alien conversations, going back and forth. You're really just going to hear noise. And that's because a radio is really an instrument that takes radio frequencies that are beyond our hearing, our ability to hear, and brings them down into the audio frequency range. And that's probably an overly simplified view of a radio. However, it works. I mean, that's basically what it does. If you point your radio telescope at a natural radio source, like the sun, for example, all you're going to hear is a lot of static. You're going to hear the audio equivalent of the ant races, a hissing noise. But that hissing noise will get louder and softer depending on what that natural radio noise source is doing. In the case of the sun, it can get quite violent, and it can get quite loud, and then drop right off again. The kind of telescope that we're going to be talking about today is called a radiometer. And it's just one antenna for one receiver, and all we're really concerned about is the power of that audio signal that's being derived from the RF frequencies that it's receiving. And we're going to watch for increases and decreases in the amplitude of that noise, if you will. This right here is an example of mine, actually, from my radio telescope, that the project I'm working on now, which is I'm studying the ionosphere. This is 24 kilohertz. It's a signal that's coming out of Maine, and when the ionosphere gets disrupted, it drops and raises in height, and by hundreds of kilometers sometimes. It's really fantastic to watch the graphs. But when it does that, that radio signal then increases and decreases, and this matches 8 minutes apart. A solar flare from it was a B 1.9 X-ray burst is technically what it's called. And that caused this deflection in the ionosphere, which was registered by my radio telescope. And this is an itty bitty one. They have bigger ones that go 3 times as high and are 4 times as wide. Nevertheless, that's really what you're looking for with the radio telescope, is you're watching for the noise to either gradually increase, or maybe you'll see a spike like this. One of the noise sources in the solar system is Jupiter, and I have a audio recording here that I hope you guys can hear. It's a radio noise storm from Jupiter at 24 megahertz. which if any of you guys are radio buffs, you know that's in the shortwave band. So it's not that hard to find or hard to listen to. So here it comes. Oh shoot, sorry, technical difficulties. So did you hear the increase and the decrease in the noise? If you had been watching that on a graph, you would have seen it just going up and down like a wave with spikes all over the place. This next one is what they call a noise storm, and it sounds like popcorn popping, but again, this is at 21 megahertz. And I've actually heard that with just listening on my shortwave radio. I heard that, and I called my kiddos over. Hey, you guys got to check this out. And of course, they were teenagers, right? So, oh, Dad, that's just noise. And I said, no, it's a Jupiter radio noise storm. Gosh, this is crazy. You can't, don't you know, Dad? It's not. But yeah, I was actually just sitting there, just monitoring with my shortwave radio, and I picked that up. Not that recording, but something that sounded just like it. So let's talk about the components. Are there any questions at this point before I move on?
I have a question.
Okay, Alex, what do you got?
Is the recorder visual and audio?
It can be. It can be. Depends on which recorder you get.
Okay.
This can record noises, and I've used it to troubleshoot radio frequency interference, or what we call RFI.
Okay, thanks.
Good question. Thank you. So let's talk about the receiver. It's the first building block, and it's probably the most common one that everybody knows. Here's a list of some of the hardware that you can get. AM, FM, here's the radio bands, and here are the frequency ranges. Believe it or not, you can do radio astronomy work in these ranges. I've done some work in the AM band, and but the problem is, of course, you have to find a quiet spot. You have to find a spot where the radio station is over the horizon and you can't hear it, and that can be kind of tricky. But if you do, you can use your AM or FM receiver. Of course, shortwave, I've already talked about that. You can use that. I've even used the audio from the television. It didn't work very well because of what you're going to see next in red. You have to be able to disable the automatic gain control of your receiver, of your hardware receiver. If you cannot do that, you're not going to see those fluctuations in the noise, because it's going to try and automatically compensate for that rise or drop, depending on the audio output. So that left me, after I tried experimenting with all of these, and I had some success, better success with my shortwave because I could disable the ACG. What I found was the most profitable is this one that's called a SDR, or software defined radio. First off, I want you to point out something to you, that the frequency range on it is enormous. You can go anywhere from 24 megahertz to 1.7 gigahertz. That's a lot of radio frequency space to explore. And there's even some that you can, by changing certain parameters, you can take them down to 10 megahertz. So it makes it even bigger. And I'm not sure how many of you guys know what an SDR is, but a lot of people think that this dongle right here is the SDR, and it's not actually. It's called a dongle. And what this dongle has is the RF stage of your radio receiver. And it's all right there in this miniaturized electronics package. And they're very cheap, $20, $20 to $30. There's some that are as high as $400, but I've never seen the need to go over $30 in buying one. So it's very inexpensive. And as you can see, the USB here, it plugs right into any USB port on your PC. A lot of times the PCs these days are coming out with the drivers already pre-installed, so you don't even have to load drivers. I had to early on, but I haven't in the last couple of times that I've used it. And so it's this is super cheap. But the software-defined radios themselves are even cheaper because there's many of them that are free. SDR Sharp, that's the one that I use currently with my ionosphere project. And I have used this other one, HDS DR. And those are free. You just have to download them and load and then install them on your PC. Right here are a couple of great resources for you. It's the same site, but they broke it out into software-defined radio and dongles. And Jack, like we talked about, I'm going to go ahead and put those in the chat.
Perfect. Thank you.
Yeah. I figured you guys want, let me see, where's the chat?
And there's actually a question in the chat as well, talking about gain. So while you're finding that link and about to put it in there, the question is, when you amplify a signal, you're injecting increasing noise. So often that's not ideal, or you would at least prefer to be able to adjust how much gain you're using, if any. I guess the question is, how much gain, do you actually have in there, and how do you find that it is affected by any extraneous noise?
Yeah. So how do you determine how much RF gain to use? RF, pure experimentation. Sorry, I can't help you with that. You have to play with it. And I do admit that it is a painful part of setting up your radio telescope, is understanding, okay, let me see, if I don't have my RF high enough, I never see any fluctuation, no matter what happens. Or if I do have it too high, I'm overdriving everything. And then, of course, I don't see any fluctuation. So it's not easily done. But I know this much: if you have automatic gain control on, the RF stage just immediately takes it out. Or I mean, I think it's the audio stage takes it out. So you just get basically a very flat line across your recorder, and it's of no help or use. And with these software-defined radios, it's easily disabled because in here there's a little switch, a software switch. Did I answer the question?
Yeah, I think we're good.
Okay, great. Here you go. Let me get that out of the way. All right. So yeah, so those are your receivers. Here's your dongle. Let's talk about the SDR and the dongle and why it's so powerful. This right here is a screenshot of an SDR. It's 196 megahertz to 200 megahertz. And you can zoom that in as deeply as you want to, or you can zoom it out as far as you want to. And what makes it so powerful is the fact that when you're hunting for a quiet spot on the radio spectrum, this right here will give you a visual to let you know. You don't have to listen to every single spot. You can quickly, right here, you're scanning 4 megahertz of space, and you see, here's this one man-made signal at 198, and I want to avoid that because I want to listen to cosmic noise or noise from Jupiter or solar noise or whatever it is you choose. Here's another way of looking at it. Right here in red, you don't want to try and monitor anything there because you're going to get interference from the sidebands of this transmitter. So you want to listen to something out here, and you want to watch it too, by the way, because if you camp on 197, for example, there can be a radio that does intermittently transmit at 197, and you don't want to be there if it is. So you're going to have to camp out and watch 197 for a while, or 196.5, or whatever frequency you choose. But the good news is you can watch it easily with this waterfall. This waterfall is intensity over time, and as you can see, the signal is getting stronger as time goes on. And on this one, the signal strength has remained constant throughout. So you would watch for lines to show up here. Sometimes it might be a dash. Sometimes it might just be a start of a line. And then, of course, you'll see the bump. Any more questions?
Yeah, there's a question from Jeff in the chat. He asked, how do you know the difference between regular band or frequency propagation changes and a source of interest?
Oh my gosh. PhD? English, please. Basically, how do you tell the difference between something that might be man-made, I guess, and
Right.
versus something that's natural?
Yeah.
You really have to observe for a while.
Well, actually, what I was thinking of, if you're familiar with 14 megahertz, it shifts right during the day and the evening, depending on the gray line as it comes across the world.
Mm-hmm.
And so how do you know the difference between that modulation, if you will, which is really just a propagation change, compared to something you're receiving from outer space?
Yeah, well, that's
Same answer.
Well, it is, and it really my first when my first shot was listening to Jupiter radio noise, right? But my second project was the sun, and I was listening at 20 megahertz. But there was this repeater that just kept coming in intermittently, and I kept seeing these things on the graph, and I kept thinking, oh my gosh, wow, I've seen something. I'm seeing the sun doing something amazing. But then, as Alex pointed out, is there a way to record this? And so then that's when I found a way to record it using that recording software. And I realized, no, that's a man-made interference right there. That's a repeater. I know what a repeater sounds like. And yeah, so there's a repeater that comes and goes over time. And I think some of that had to do with the ionosphere, to be honest with you, because I think the repeater was over the horizon as infrequently as it happened. So yeah, you just have to kind of camp and just make sure, all right, this is completely free of any kind of radio frequency interference, whether it be man-made or maybe even natural.
Can I insert a comment?
You may.
Tim Denman and I brought students to the Green Bank Radio Telescope in West Virginia.
Oh, wow.
It's the world's largest steerable radio telescope, or at least it was when we brought the kids there. And one of the things they did was they would travel around the county, and maybe Tim remembers how they actually did this, to find man-made interference. Like maybe they had a small radio telescope that they brought around with them. I don't know. But the one interference they found was a woman's dog in the doghouse had a heating pad, and there was a short circuit in the electricity.
Oh, yes. And there's a great story about that too, on how they found the radio noise from Jupiter, by the way. A radio astronomer named Burke was tuning his radio telescope, and they kept getting this noise at 20 megahertz, and they didn't know where it came from. And they theorized, oh, it must be some yokel down in the valley there. He's got his cars not tuned properly, and it's the ignition coil is giving us this frequency, right? And yeah, but they pursued it, and they realized, no, wait a minute, this is coming from Jupiter. And that's how they discovered the radio noise from Jupiter. So
They also used only diesel cars on the campus where the telescope was, because gas cars
yes,
give off radio waves.
yeah, the ignition does. Oh my gosh, it's so true. Yeah, so that's a joke that I've had to myself. There's really nobody that understands this joke, but once you become a radio astronomer, you're really a RFI investigator. Because that's what you spend your time doing. You're looking at the graph saying, oh my gosh, where'd that come from? Oh, and it turns out, the wife's cooking dinner, and it's the stove, and it's, creating noise on your graph. But yes, thank you. Great stories. And you highlighted the problem of being a radio astronomer right there. So here's another example, and it's in the middle of the RF band. Notice all the different peaks. This is Radio Romantica 98.1, whatever. This is your oldies station or something, but these are all man-made. And if you're trying to listen here, it becomes challenging. But you can, if you get in one of these troughs. If you notice down here, it's very dark. Well, not very dark, but it is darker. And that means there's no broadcast at that frequency. Or if it is there is somebody broadcasting at that frequency, they're over the horizon and it's not getting to you. It's not the ideal place to try and listen for a natural noise, but it is possible. I also want to point your attention over to here. This is a SDR, a radio, software-defined radio. It's the one I use. And there are all kinds of functions that you can do with this. You can change the bandwidth. You can change well, it's basically a radio. If any of you guys are ham radio operators, you recognize all of this stuff. And this right here, automatic gain control, you recognize that? Yeah, you can turn it off right there. So next, I want to talk about antennas. Is any other questions or comments, by the way? Okay, so antennas. This is the most technically challenging part of any radio endeavor. This requires a lot of mathematics, and you really got to kind of know what you're talking about when it comes to building your own antennas. However, I would say that if you're going to buy an antenna, somebody's already done the engineering work for you. You just need to buy an antenna that is going to do the right or be tuned to the right frequencies that you're looking for. So the basics, the purpose of an antenna is to convert electromagnetic energy of the radio wave into current, because these radio waves, their energy is not in the form of electric current. It's in the form of electromagnetic energy. So you need a piece of wire for the electromagnetic energy to cross at right angles to induce a current into that wire. And that's how we get our signals. That's how we get our FM radio, and that's how Bluetooth works, and all the rest of it. It's that same principle. There's many types of antennas. You have your vertical, or think spiral or whip. This is what's on the back of your cars. CB radios use these. Then you have dipole, which is up here. Think rabbit ears. Rabbit ears are just basically foldable dipoles so that you can put them in a V pattern or lay them flat if you want to. Yagi is another one that's more directional. Yagi is hard to use though, because it's really tuned for one frequency. And so it's not very useful. There's another one called DSP. What is it? What is that? Oh, sorry, it escapes me. But it has more of a range of frequencies. And it looks like a Yagi. In fact, many people get them confused, but it has a wider bandwidth.
I'm sorry, excuse me, are you talking about the LPS, the log periodic steerable?
Thank you.
Okay.
Log periodic. For some reason, I couldn't remember that. I don't know. But yes, that's the one. And I should probably update my slide and get rid of the Yagi, because I don't know that the Yagi is going to be useful. Unless, of course, that's the one frequency you want, right? I don't know. There's parabolic, which of course everybody knows about the parabolic. That's the one that is always identified with radio astronomy. And then there's the loop antenna, which is down here. This is actually my antenna. It's in the basement of my house, and it's tuned for 24 kilohertz, which is just outside the audible range of the human ear. So let's talk a little bit about the antennas. Here you go. If you have an FM receiver, you want to use an antenna designed to capture those frequencies. But you also have to use the orientation for that frequency. So this right here, this part, it works best if you have the wavelength of the frequency, if it matches the wavelength of the frequency. I'm sorry, I'm stumbling here. That we're going to talk about in the appendix, because that's where it gets technical. But these antennas here are directional. So if you look at the spiral antenna, what this is telling you, the polarization is horizontal. So the signals have to strike it this way, or else they won't induce current into the antenna. If they come from the top or from the bottom, they're simply not going to induce much current or any current at all. The dipole, the signals have to come either from the bottom or from the top. If they come from the side here, it's not going to induce current again. And same with the Yagi, it has to be coming from this way. If it's coming from down below or up above, it's just not gonna, you're not gonna get anything. And of course, parabolic, it has to hit the reflector and then go to the antenna there that's in the middle. And if you'll notice, that's a vertical antenna here, and it's being fed by the reflection off this dish. So you can combine these two, right? You can put a dipole at the in front of a parabolic, the focal point of the parabolic, and you can make your own antennas, which later we are going to see some of that. So here's more text to describe kind of what I just talked about. And that, any questions about this? Okay, like I said, there's more in the appendix. If we have time, I'll cover it in more detail.
I have a question.
Okay. What do you got?
I'm wondering if you can say something about the angular size of these antenna patterns, like compared to a telescope that can see the full moon or see Jupiter.
Okay.
If you're listening to Jupiter, can you really focus in so it's just Jupiter in comparison?
Okay, so yeah, and you can. The short answer is yes. The long answer is very complicated. There are ways. In fact, it's called the Radio Jove project. I don't know if you've heard of that or not, but they use a dipole antenna listening at 20 megahertz, and they have all the designs and specs and everything you'll need on their website, and they discuss that, how to steer the reception of the dipole. And you have to use capacitors to change the phase and angle with which it's received. but it's complicated.
So
I have a,
I was just going to follow up. Does the parabolic, you're saying the parabolic gives you a tighter beam width than Yagi?
I believe it does. It's a higher gain antenna for sure. And
Okay.
and when you're talking about antennas, everybody, gain isn't the same as amplifier gain. Okay, it just means it's more focused in its reception.
oh, okay.
Yeah, so be careful of that.
Quick question. Can you hear me?
Yes, I
About
hear
the
you.
Yagi, the Yagi
Mhm.
could that be tuned for 21 centimeter radiation?
Sure could.
Have you done it?
No, I've not experimented with the Yagi, but some of the Yagis for the very low frequencies, they're huge. They're feet long, you know, I mean, they're, you know, 10, 15 feet long. And these directors, they're called right here, they're 3, 4, 5 feet. All right. And they're kind of hanging because, you know,
Okay.
they're metal. And so they're kind of sagging a little bit. And these things can be very large for very low frequencies. But yeah, you can tune them to anything you want. You just have to.
Hydrogen has this 21 centimeter line. So that's 1.4 gigahertz.
Okay, good. I forgot what that was. 1.4 gigahertz. Thanks.
Yep. Which is very low frequency. That's you'll
Gigahertz?
need a very,
L band.
I'm sorry, what is that?
L band.
L band.
That's pretty high.
Oh, I thought you said 1.4 megahertz, not gigahertz.
Oh, no. Giga.
Yeah.
Oh, gigahertz. Never mind. Okay. So I heard you wrong then.
Yeah, I'm sorry.
Okay.
1420 megahertz.
There you go. Yes, that's very high. So you wouldn't need a very large one. Right.
So, Kevin,
Sure.
which antenna would you use to build a mobile setup for meteor detection?
Hey, Jim, how you doing?
How's it going?
Well, the ones that I've seen online are dipoles that are, they have two of these at right angles. So there's one that's coming out of here, you know, coming towards us, and one that's going away from us. And they, between those two, any meteors flying across the sky, any kind of ping that comes off of the radio station that they're listening to is recorded.
Is there a particular length?
Well, again, that depends on this frequency.
Okay.
Because the wavelength of the frequency, to give you in brief, you want this long enough to capture the full wave or half the wave or a quarter of the wave or one of the harmonics, in other words.
Okay.
Right. So if your antenna is too short, it's not going to capture enough electromagnetic radiation to produce enough current to really give you a good signal. So, but to answer your question, the length would be somewhere in the FM band, because this is kind of getting off topic a little bit, but the meteor detection is, well, how do I describe this? It's done by selecting a FM station that's over the horizon. And so those radio waves are actually flying over your head. And then what happens is the meteor comes flying through, it ionizes a trail of, well, it creates an ionized trail of gas. And then that radio signal that normally would have just flown over your head at, 6,000 feet hits that ionized trail of ions and reflects down into your receiver, and you hear a ping kind of a thing. So it will be in the FM band because of the fact that you're using FM stations to capture the transit of the meteor.
Okay. We'll talk more on it later.
Yeah. There's lots of websites out there on how to do it, and there's even some websites out there that you can just kind of tune in and listen to what they're doing.
Okay. All right. We'll talk more after the presentation.
Okay. All right. And that'll work good with your camera, right?
Yep, from the last
Yep.
discussion we had.
Yep. It'll
Okay.
work great with that. All right. So the recorder. This is the part that's probably the mystery to everybody. It performs the same job as a camera in optical astronomy. It basically records the noise level graphically. And in the olden days, they had these strip chart recorders. You see right here, that's Richard Jansky. And they had an arm with ink on it, and it would just move back and forth. Think seismograph, right? Like the old seismographs. And that's how you would record an increase or decrease in the amplitude of the radio noise. And below here is an example of it, an application called Radio SkyPipe. Now, Radio SkyPipe, they have a free version, which is very useful and very good. I used it for a number of years before I actually purchased it. Let me get that. Let me get that in the chat. Chat. Where'd you go? Chat, there you are. Okay, so here's the link for Radio SkyPipe. Very useful, very helpful. No more long strips of paper with ink pens dancing around on them. It's all done electronically now. Here it is. This is straight from the website. Free version. It has limited features, but you know what? I found them very, very useful, even though they were limited. You definitely can get going on the free version. I went ahead and I purchased the this one right here for home use because there was a couple of features that I wanted with it, but you don't have to. You could take the free version and probably go a long time. And as you can see, the commercial industrial, boy, it gets kind of expensive there. Or for educational, no, it's the same, 50. But you can collect the data and you can store it on your PC. You're really using the sound card on your PC because what happens is the like I said, that radio frequency is converted to an audio frequency. And as that radio frequency increases, well, then the audio level, or excuse me, not the frequency, I'm sorry, but the radio noise level goes up on the radio frequency level, then so does the audio, right? So there's your sound card is simply being tapped into by Radio SkyPipe, and that's all it does. It just kind of taps into your sound card and listens, and when there's an increase in the noise, well, then the graph goes up like this. Very simple, very easy to use. It has lots of features here. And one of them is that you can actually connect, and that's why I put this down here, is you can actually connect to other observatories around the world to see what they're hearing. You just connect over the internet, and then this graph that would be on this screen would be from that observatory. Very helpful, very useful in trying to see what others are doing and whether they're picking up changes in the noise level the same as you. So any questions about that? It's probably brand new. You've probably never seen anything like this.
Have you used this type of software on a Raspberry Pi before?
No, but that's the second time I've gotten that question.
I'm kind of curious about maybe setting up something at our star parties that would make an audible ping whenever a meteor went over, that people would know they're coming, if they're going over their heads.
Yeah.
That
So
would be compact,
So does the Raspberry run on Windows?
I think there's ways.
Does Windows run on Raspberry, I should say?
Yeah, I'm not 100% certain.
No, but it runs Linux. Sorry, it runs Linux, but it also does SDR Sharp runs on Linux.
Okay.
Uh-huh. Okay. Sounds like you already know that. Good.
And-
Yeah, I
And Steve,
think-
that's something I'm actually trying to work on now.
Oh, okay.
okay. You two can get together.
That sounds like a great project.
Yep. I believe this is Windows only though. So you'd have to use Wine or something. Windows, what is it? Wine stands for Windows in Linux, or I can't remember what.
Some kind of emulator. If you're
Yeah,
gonna
some sort of emulator or virtual machine, Windows virtual machine inside of Linux. I'm not sure how
find
that
a
works.
Linux package or something. Yeah.
Yeah, but I believe at least the last time I checked, this right here is only Windows.
Okay.
But no, that's a great thing because I've been working on a mobile version of my radio telescope for years. I haven't quite perfected it yet, but yeah, I definitely want to be able to just pick it up and go out somewhere and use it. But so right here, this is putting it all together. This is an example of an SDR setup where I use two PCs. One of them is running the software-defined radio, and the other is running Radio SkyPipe. And you take the audio output of this PC and you plug it into the audio input, the microphone jack, if you will, and voila, you've got a radio telescope. Of course, this PC you have to insert the dongle and an antenna that's tuned to whatever frequency and aimed at whatever noise source you want to pick up. But yeah, once you do that, you've got yourself a radio telescope.
Just so you're aware, sorry, there's actually a virtual sound driver that will let you link the sound input and sound output on the same system.
Ah, sweet.
Yeah. I've used it for a couple of things associated with SDRs. I'll see if I can find the link and post it.
Yeah.
But it actually lets you virtually, it's a virtual connection rather than a physical one. And so you can do everything on the same device.
Yes, that'd be perfect. Now, I never did that because I was always so cheap. Sorry, I was just cheap. I never had good quality computers. I never had, high CPU speeds and things like that. So I just went with two different computers. But if you can come up with something that has high enough CPU and memory and other specs, go for it. It might just work.
Yeah, I think it's called, and I think Jeff just posted it actually. I think it's called virtual audio cable. So I think that's in the chat.
There it is, vb-audio.com/cable. Something to try now, something else for me to mess around with. So any other questions, comments?
Yeah, I just looked it up. Raspberry Pi can now run a stripped down version of Windows 10.
Ah, there you go.
Yeah, but I think it's the IoT version of Windows, not the desktop version of Windows.
Right, the IoT, not desktop.
So
I linked the article from February 9th, 2020 in there.
So maybe missing some drivers or capabilities then. Yeah.
well, the big question is, can it run Radio SkyPipe?
Right.
Or your SDR, whichever one you're planning on.
So SDR Sharp, doesn't it also have a recording facility to?
If I remember right, it does.
But it's big. I mean, it's getting all the frequencies in your band, so it's a lot of storage to record all of that.
Yeah, I've only used it was either here or it was here. I can't remember which one of these ones I did the recording on to find the RFI. But yeah, what I did, there was a way to trigger. I believe it's on this radio SDR Sharp, where you can set a threshold. If the signal goes above a certain level, start recording, and then when it goes down below a certain level, stop recording. So that way, I could just let that RFI jump in there and do its thing, and then I could go back and say, all right, well, I've got 5 captures. Let me listen to them. And that's when I realized, oh man, this is a repeater. Oh boy. So I'm pretty sure that was on SDR Sharp. It's been a while since I've gone down there and messed with my radio, right? Once you set it up, you just leave it alone. Don't go in there. Don't change anything. If you do, you're going to have to start all over again. But yeah, I believe that's where it was. Okay, so tips and pointers. You have to be careful about the output level of your radio. We talked about this earlier. This output coming into this input, you have to be careful. You want this to be as low as possible, but yet not so low that it's not going to actually, the increases and decreases in the audio noise are not going to be missed, right? So you need some amplification on this, but it can't overdrive your input here. That's really important. And I've spent a lot of time tuning these guys just to make sure that, okay, when I get an increase, it's registered over here. And when I get a decrease, it's registered over here. And the way I do that is I pluck the antenna out of this. It's primitive, right? But it's an old radio troubleshooting technique where you pull the antenna out and the signal, RF signal drops, and then your intermediate frequency stage lowers, and then your audio frequency goes down, and then you should see over here on your graph, it drops. And if you don't see a drop, then you know you've done something wrong here with this, and you need to tune this so that it's lower or higher, depending. Does that make sense? I'm not really sure. It's something that unless you've done it, it might not make sense.
Yeah, it makes sense to me.
Okay.
So you might actually see a decrease in signals for some reason as well?
Yeah.
You mean above the baseband noise?
Yep. Yep. I have seen that before.
Okay.
It's not usually, and if I showed you the graph of my this 24 kilohertz signal over a 24-hour period, you'd see it go way up here at night for when the ionosphere, you know, the F2 is active, and then it just comes down, and then it comes up, and then as the sun rises, it goes to a certain level where the, you know, after the E layer forms, and then it just goes there and it stays pretty much in this level until evening, and then it drops down, and then it just goes back up again for the evening. So yeah, it just kind of depends on what you're really looking for and how you're looking at it. But yeah, pluck the antenna off and you should see this drop down. We already talked about RFI. I call it HMS sometimes, ham radios, microwaves, and stoves. These stoves, they just cause all kinds of noise. Looks like lightning. Potential projects here. I think we've talked about this one, decametric radio noise from Jupiter. You want to look up the Radio Jove project. They've already done a tremendous amount of explanation and documentation on how to do that. Radio emissions from the sun. That was my second project. The counting meteors during a meteor shower. There's Jim's working on that project right there. Here's one that I think I'm going to try next, and that's cataloging the frequencies emanating from Galaxy Center. Radio noise was discovered at 20.5 megahertz. So who knows what else what other frequencies are out there? Actually, I think the scientists do, but I don't. So I was gonna, work on my antennas and get my logarithmic dipole periodic, or no, what was it? Logarithmic, periodic. Shame on me. I should know this. Anyway, I was going to get my antennas, and you need various antennas to start down here at the 20 megahertz range and go all the way up through the gigahertz range. So that's going to be a big project where I'm going to really work on my antenna skills. And then there's another one, coordinated optical observations of Jupiter in conjunction with the decametric radio noise. There's a theory out there that the bands around Jupiter are actually caused by the electromagnetic field of Jupiter, which is very powerful. And so it would be interesting to see if the radio noise corresponds to changes in the clouds, or maybe there's a formation of a white oval during a radio noise storm, and then that oval goes away in conjunction with the radio noise. So that one, of course, would require a good telescope with a solid mount, and you'd have to have all kinds of cameras and filters to spot all that. So that's going to be out of my league, but who knows? One of you guys could do it. Also, there's other projects out there that I haven't even thought of. So be as creative as you want. Okay, and now is the appendix. How much time do we have? I can't, okay.
You can use as much time as you need, but it's 4 minutes to 9.
Ah, okay. So I'll just hurry through the early beginnings because I think I already covered this. In 1931, there was a radio engineer at Bell Laboratories named Carl Jansky, and I've already told you his story. But he was looking for noise that was interfering with AT&T's radio transmissions, and they hired him to find them. And he built this antenna, and it's a dipole antenna. And basically, what he had was the equivalent of a shortwave radio of today, with this dipole antenna that was on wheels, and he could move it to any direction he wanted to. And like we talked about before, by changing the capacitance and other things, he could bend the reception of that antenna to point it. Here's another picture of it. But again, there's just nothing fancy that's needed to do this.
I'm wondering if that picture is from Green Bank, West Virginia, because that is there, or it's a really good model of it.
Okay. This is a replica.
That looks like the dining hall behind it.
Wow. Really, this brown structure back here?
Yeah, brick building.
Huh. Okay. What do you know?
Maybe. I haven't been there in a long time.
I bet you we could find out where it is.
Mhm.
Here's a radio block diagram. So here's your RF stage, right, with your RF amplifier, and that would be taken care of by the dongle with the mixer in there. Then here's your your IF frequency, your intermediate frequency, and that's taken care of by your software-defined radio. And then here's your audio stage, your audio amplifier, and that's taken care of by the sound card PC, the PC sound card, excuse me. Just kind of showing you, there's your radio, and this is how it's made with the software-defined radio. Here's the antennas. We already talked about these, this slide right here. But back to the wavelength of the frequency, you have to make sure that your antenna matches that in order to get your best reception. This right here is a illustration of a dipole, and this orange right here is the voltage being induced by the electromagnetic waves hitting it. The blue is the current, and as you can see, it's going up, going back, going up, and it's changing polarity, minus, plus, minus, plus. And this right here, of course, would be your receiver. But the wavelength is really important, because the higher the frequency, the shorter the wavelength, and the lower the frequency, the longer the wavelength. And they're just waves. And just imagine that wave has to fit on that wire all the way. And so depending on what frequency you're dealing with, depends on how long that wavelength is. For example, we'll just say 100 megahertz, right? That's dead in the middle of the FM band.
This thing, whoop, I'm sorry, I lost you there. I didn't know if anybody else did, so.
Oh, can you see me, or you can't
no
hear
audio.
me? No audio. Can you hear me now? Hello?
I can hear him.
Yeah,
I can hear him.
I could hear
It's
him.
me.
Oh,
I just
okay.
got a note my internet connection is unstable, so I'll go away.
Well, don't
Go
go
away,
away.
Jack.
Just fix your internet connection. All right. Yeah. So here it is, right? FM, and if you look at the full length of that FM wavelength, it's 9.5 feet, which is, yeah, I mean, that's a big antenna, right? A big dipole antenna, but you know, it's doable inside, right? Kind of a big antenna. But if you look at the antenna for 510 kilohertz in the AM band, it's 1900 feet. All right, that's crazy big. You're not going to be able to fit that in your house, right? And so it seems like all is lost, right? But yeah, there goes my technical difficulties. They also work. Antennas will work at half length or quarter length or 1/8 length. And so you don't need that full 9.5 feet for that FM antenna. In fact, it can be 4.7 feet, 2.4 feet, 1.2 feet, or even 7.25 inches. And if you look at your portable radios, they have that telescoping antenna. That's what it's for. It's for catching that frequency just at the right length. And so if you're having trouble with a distant station and you know what frequency it is, you can adjust the height of your telescoping antenna to tune it to capture the right wavelength and increase the gain of the signal. Very few people know that. Very few people do that. They just kind of take their antenna and fully extend it, but it's really designed so that you could collapse it to the right length. And also the length can be coiled up too. It doesn't have to be like a telescoping antenna or a dipole. It can just be wires that go round and round and round. This right here is my antenna in the basement. It's 540 feet of laminated copper wire, and it's like 1/64th the size that it needs to be for a 24 kilohertz wave.
Is that an amplified active antenna?
No, it's not active, just passive. And I'm actually using my sound card instead of a SDR, right? Because the sound card doesn't care where that frequency comes from, whether it's actually in a microphone that's picking up audible,
Sure.
and changing it to electrical, or whether it's just electrical itself. So it works good. I pull that antenna and I watch my SDR go flat, and I plug the antenna in and I see all the peaks from all those very low frequencies. Right here is a great wavelength calculator that I found online, and also basic antenna theory. So I'm going to put those in the chat as well. Any questions about what we talked about?
Have you done any directional stuff at all? I mean, most of this seems to be pretty broad spectrum. Have you actually looked at any kind of tracking?
No, I've not done any direction. Well, that's not true. My third project, I was using a microwave radiometer using an old satellite dish, and yeah, that was very directional.
Thank you.
but I could not get a portable version. I really needed a portable version that I could point, because I was studying the microwave emissions from thunderstorms, and with it fixed, I had to kind of wait for the thunderstorm to pass in front of it. And so I said, no, I need to develop a mobile version of this. I just couldn't get it working, and I gave up. But yeah, the version that was of my radio telescope that was fixed, pointing north, boy, that worked great. Every time a thunderstorm passed through, I'd watch that microwave increase.
Thank you.
Sure, thank you. So here we're getting into just antennas that people have made. This one right here looks like the, I don't know, a barbecue grill or something, you know. But as you can see, it works. Somebody put a low noise amplifier right on top of it. C-band, I think that is, or is that L-band? No, it's an L-band. And they're looking for the hydrogen line right there. And there you have it, right? Just sitting out there on the patio. There's an antenna for you, homebrew. Works good. Here's another example of an antenna. It's radial. Notice the chicken wire as a reflector. And notice the shortwave radio, tuned to 21 megahertz. Very simple, very effective. Probably cost $20, right? Here's one. Definitely bound to create, what is it, QW? When your wife says, get that thing out of my backyard, because it's ugly. But yeah, you can see the whip antenna there, and these are the reflectors. So
That's a corner reflector.
Is that what it's called? Corner reflector?
I think so. And it has the property that it reflects back at the same direction that the wave came in. I don't.
Oh, so it's actually reflecting back.
Yeah, I don't know why that would be. I mean, the astronauts put an optical corner reflector on the moon so that they could bounce lasers off without having to arrange it exactly to point exactly back at the Earth.
Exactly. Yeah, because it's coming in at a right angle. It hits here, and then it goes right back. Exactly.
But why? Well,
it's three-sided, right? So it could have the effect of focusing some of the signal on the vertical.
Instead of reflecting it back, it may be that those two sides put it onto that third side, no matter what direction. So this may be. I want to learn more about it. I don't understand right now, but it makes me think of a corner reflector.
It looks to me like a cheap version of a parabolic reflector. You can't make a parabolic, so you make a corner. Yeah,
possibly. Yeah, that might be.
There you go. I'm putting these slides in here just to show you, hey, be creative, right? I mean, this is a vertical with a corner reflector. There you go. It worked. I think that's why it's there. Here's another one. This guy is from SETI. But notice this reflector, right? It's just a great big V. I don't know what angle that is. But in here is a 2-element, what would that be? That's not Yagi, it's a
dipole.
dipole.
Yeah, 2-element dipole. There you go. And then he has a reflector to amplify the gain, amplify the signals.
And that gives it directional sensitivity also.
And thank you. Yep. High gain, right?
Yeah.
And so, and there he is. He's actually going to point it at something. So my wife would kill me if I had that in my backyard, but
My mother-in-law would be growing plants on that before I knew it. Running bean poles up it.
exactly.
You could
Plants
disguise
growing on it whether you wanted them to or not.
You could disguise it growing grapevines on it.
Yeah. Because I don't think the biological matter would change the RF at all.
Yes, it does. It absolutely does.
Does it? Okay.
Yep.
All
It
right.
actually creates, in contact with metal, it creates a lot of electrostatic interference.
Oh, right.
Yeah.
Well, living things, they do generate that. That's correct. I have pointed my microwave radiometer at a tree.
Yep.
And noticed that tree is generating microwaves. So yeah, that's a good point. I'd forgotten that.
So wrap your trees in tinfoil before you start.
Or just don't point your antennas at them. I mean, gosh. All right. So that's the end. That's the end of my presentation.
Oh,
Excellent.
thank you.
So, no, thank you.
Thank you very much, Kevin. That was really fascinating. And with the little bit I know of radio astronomy, it really educated me. And I nominate Steve to create something that we can hear meteors out at the star party, since you asked the question.
I'll bring my piano.
So if anybody makes it to Green Bank, you too can have a cool button.
Cool.
Ooh.
I'm going to be in the area next week, so I might drive down and get it. No, I'm just kidding.
Oh,
I'm not going
really
to be
out of the
renting a
way.
car.
It's very, very in the middle of nowhere, and that's
okay.
on purpose, of course. There's
Yeah.
a ring of mountains around it.
Ah, yes, of
Here's
course.
a cell phone, right?
Is that the one with the old 1930s gas station in the middle of the town?
Oh, yeah.
Yeah,
Yeah.
yeah, with the
It's-
general store.
When I was down there, I was down there taking on a photo trip one time, and there were 3 other photographers in the car, and they said, "Jeff, go ahead and pay for the gas." So I went in to pay for the gas, and I come running out, and I'm like, "You guys have got to come in here and see this thing." And these people were great. I mean, they let us spend an hour in there taking pictures of their country store.
Yeah. Terrific.
Yeah, they had bicycles on the campus that the students could borrow. Of course, the only place to go was the general store.
I think there's 2.
Maybe.
It's a perfect field trip because they can't get in any trouble.
But
There you
Kevin,
go.
Kevin, you're probably a lot closer to Socorro, though.
So I have a question about how much time you spend doing radio astronomy. Can you just like set up your recorder and walk away and come back later and look at the record of what it recorded?
That's a great question, because when you're setting it up and tuning it, you'll spend a lot of time.
Right.
Spend a lot of time. It took me 6 months to get my this project that I have going now with the ionosphere. I had a lot of different components. I have everything connected via Wi-Fi, and so yeah, that just took me forever to get set up. But once I got set up, now I just go look at the graph every now and again and say, okay, radio burst here, I better research that, and no radio burst on this day, no radio burst on this day. And so
So are you retired and you just spend all your time doing radio astronomy?
no, no, I'm not retired. I'm tired.
Not retired.
Yeah. Speaking of which, Jim, I got to call you and talk to you about the change in my job position.
I already heard.
You already heard? Okay.
Yeah.
Who told you?
Your boss.
Oh, really? Okay.
Yep.
Okay. Well,
Anyway, to go back to the radio astronomy stuff, I have the all sky camera behind me, which I will be testing Thursday night at Island Beach State Park. And one of the intentions is that we have 2 radio guys in our club down here in New Jersey. We want to work on a mobile meteor detector setup and have both of them running at the same time, and then create a audio video combined video to post on YouTube of the 2 of them in sync.
Oh,
So that's something we're trying to do. I just got to find the right documentations and material, for them to look at it with the mind of keeping everything mobile.
Sounds like a great presentation for Mid-Hudson astronomers.
Yeah, eventually, if I can get it working, I'll share it with you guys.
Can you put on the chat your email or something so I can be in contact with you? Please?
Sure.
He's on
I don't
Slack.
know how long a project this is gonna be. when
Oh,
you-
it's just gonna be a while. I may have to wake our members up on our end and remind them that, hey, you guys are still interested in doing this, right?
Well, we'll still be looking for speakers a year from now.
Okay. Well,
Thank you.
I've got a number of subjects that maybe we could talk about. I just wrapped up on asteroids with our club. And I got 4 presentations that I'm going to be doing for the county parks down here. So we could always insert one of those into a discussion.
Yeah,
Awesome.
you can hone those down to perfection, and then we'll get to see it. So Alex, he's on Slack, by the way.
Yes, I am.
Okay,
Jim is on Slack.
awesome.
Yep. And that's my personal email address. If you want my club one, I can send you that one too.
Oh, personals works.
Okay.
Yeah, Jim, I'm looking at a web page right now about it. There's a lot of them. There's a lot of web pages about that.
Right. We would end up probably having to use definitely a laptop to a dipole. And it would be nice if we could make like a Raspberry Pi setup just to have it all sit on one tripod. You know, but we'll see.
Yeah, well, the good news is FM, right? So FM means you just don't need a big antenna. Yeah, there you go. This one right here. They're using a dipole on a tripod. Yep.
I don't see it.
Oh, I'm sorry. Let me share my screen. Ah, where'd it go? Hold on one second. There we go.
Okay.
See, and then he's got his dipole right there.
Directional on the tripod.
Mhm.
Send me that link if you can.
Yes, sir. Not a problem. And then, you know, where was it? It's further down. I think they have the, no, this is a different page, but yeah, you can see there's a meteor strike there. He has a different, he has Spectrum Lab.
Right. Now I do have a sample YouTube video on hand.
Mhm.
If you guys want to see what I'm talking about, you know, if you want me to share it.
I do.
Yeah, sure.
Okay. Let's go here, share my main screen, and move some of this stuff out of the way here. Now this is coming from YouTube, so it may get a little choppy.
Different fireballs. Do that. Listen to what we have here.
I'm bringing it into where it actually is.
So what we will have heard there was 4 different meteors.
That's pretty much all it is, you know, an all sky type camera, and you know, the radio hits from the meteors going by.
That was from March 15th this year.
Let me go back.
Oh, it said March 15th.
Yes, March 15th. You know what? I'll do this. Copy the link.
Hey, Jim, I put that link in the chat for you.
Okay, thank you.
Mhm. Are we still recording, by the way?
Yes, we are.
Okay.
I want to drop that.
Should we go ahead and stop? I think we,
Yeah, we're pretty much done with the main presentation,
Yeah,
right?
go ahead and cut it.
all right, now we'll turn off the Facebook stream. And wait for that to finish. Okay.
Now we can really talk.
Yeah.